Hello everyone. So today we are going to pick up one of the most important tools for integrating, for finding antiderivatives. Up until now, we have found the reverse of like the power rule. So we know how to take the derivative of x cubed and we know how to take the antiderivative of x cubed. And we've also done some trig functions. So today we are going to learn how to do something a little bit more complicated. So let's look at a problem like this. So we're looking at finding the antiderivative of x cubed plus 4 all to the fifth power times 6x squared dx. We cannot just use the power rule. It just would not work. The same reason why like the chain rule is more involved. We're going to reverse engineer the chain rule. So what you want to look at when you're working on these is you want to look for pieces that can be an inside function. So here, obviously, or more obviously than otherwise, this x cubed plus 4 is an inside function. And so, so look for an inside function. An inside function. And set that equal to u. So u is just a choice. You do not have to use u. You could use any letter you want. But you're just going to set that inside function equal to u. Now, sometimes you will be given functions where it's not obvious what your inside function is, or what you should use as your U-substitute. One of the things is look for something that looks like an inside. So if it's underneath a square root, if it's raised to a power, if it's inside of like a sine or a cosine function, or it's a power of e, then those would be kind of like a good hint. Another thing is look for things that are similar to the derivative. And so if we look at this guy, this is a good choice for u because what's its derivative? 3x squared. That looks kind of like 6x squared. So look for the thing that has a derivative-ish piece also in here. So when we are doing this, then when we replace, before we replace and do the U-substitution, I would recommend, just take the derivative. So du dx, and do it with Leibniz notation. It'll make more sense in the future. But it is going to be du dx. It's going to be equal to 3x squared. And so the last thing I want you to do is multiply by dx to the other side. So you end up with du is equal to 3x squared dx. So now your goal is to get everything that's in terms of x in terms of u. You cannot have two different variables going on when you're using U-substitution. You can only have one. So here, we're going to replace the x cubed plus 4 with u. And then we want to see if we can factor this so that we end up with the 3x squared dx. And so before we even do the replacing, let's do this. So we have x cubed plus 4 to the fifth. And then to get 3x squared dx, we need to factor out a 2. Squared dx. All right, so now we do our replacing. We do our substituting. And so we end up with u to the fifth times 2 du, because du is equal to 3x squared dx. And so I'm going to rewrite this as just something a little bit cleaner. So 2u to the fifth du. So now we take the antiderivative as usual. And so we end up with, let's see here, it is going to be equal to u to the sixth, and then 2 divided by 6, plus c. Because this is a general antiderivative, we need to do a plus c here. Are we done? No, because we want to write it back into our original form. And so we go in and we're going to say that this is equal to 2 sixths 1/3. U is x cubed plus 4 to the sixth plus c. And so if we look through this, when you take the derivative of our answer here, you should end up back at what we started with up here. But this is an example of how we might use the U-substitution. So I'm going to write these rules down on the next page so that you kind of have instructions. So how to do U-substitution. So identify the U. So your hints are look for an inside function. And then also look for something that has a derivative. Oops, let me go over a little bit. That has a derivative. Or a multiple of a derivative. Also in the integral. Okay, so those are kind of your two first hints. Just letting you know, you will pick the wrong U at some point. If this is your first time using U substitution, it's normal to pick the wrong U. It will become very obvious that you picked the wrong U as you go through the problem. All right, 2. Take the derivative of U. And so it's going to look like du dx equals whatever. And then multiply by dx, so you're going to get du equals whatever dx. Okay. 3, do a little factoring on the original problem in order to do some clean substitutions. All right, so you will want to substitute both the u and the du dx. Like you should be putting in a du for something dx. If you have not done that, then you're going to have some issues. And then 4, take the antiderivative in terms of u. And 5, substitute back. That is a very important step. The whole point is to substitute back. Now, I am going to put a little star here. This is specifically for indefinite integrals. When we do a definite integral, you can substitute back, but you don't have to, and we'll see one of those later on in this lesson. So let's go and, you know what, I'm going to put a little 6, or just if things get messy, pick a different U and start over. So that's kind of like a hint. And so let's look at the antiderivative of cotangent of x. You might be looking at this and thinking, this doesn't look like a U substitution. So what we're going to do is we're going to rewrite this. So cotangent is the same as cosine of x over sine of x dx. Okay? So at this point, we need to pick a U. And our options are basically, I've heard that some people will say x is a good option. It's not, because all you're going to be doing is changing the letters without changing the form. At the end of a U substitution, you should have changed the form to something simpler. If it's not simpler, then something went wrong. And so I am going to pick, let's see here. So the derivative of sine is cosine, and the derivative of cosine is negative sine. So that doesn't really give us a hint on which one we should pick. So I'm going to just start by saying that U is cosine of x. All right? because might as well just pick one and go. And then we take the derivative, so du dx is equal to negative sine of x. And then, so du is equal to negative sine of x dx. All right, so if we were to split this up just a little bit, so I'm going to rewrite this so that we can get this better. You end up with cosine of x times 1 over sine of x dx. All right, so if I'm looking at this, I see an issue. So what I want is to be substituting in a sine times dx, but we have a 1 over sine times dx. So we've got an issue here. And so there's no easy factoring we can do in order to make this U substitution work. So what this tells me is this is the wrong U. So let's start over. And let's pick the other option as U. So we're going to say that U is equal to sine of x. Then du dx is equal to cosine of x. And du is equal to cosine of x dx. Now, at this point, this is a better choice, because if we split this up, so we're going to rewrite this again. We're going to say that this is 1 over sine of x, cosine dx, cosine of x dx. And this is what we want, because we know that this is equal to du. This is equal to du. Sine of x is equal to u. So we can rewrite this as the integral of 1 over u du, which we know to be natural log of u plus c. And we want to go back and substitute back in terms of x. So this is natural log of sine of x plus c. So the antiderivative of cotangent is the natural log of sine of x. So, hey, that's kind of interesting. You can do the same thing with like tangent. So this might be something to try, is like see if you can do something like the integral of tangent. See if you can recreate this process. All right, let's look at this problem. So this seems to have a lot going on. We have a tangent and the secant squared and a square root of x. So I want to point out that we have a plus sign here. Remember, we can split integrals along a plus sign. And in fact, you definitely want to do that whenever you start seeing things become more complicated. And so I'm just going to rewrite this to be e to the negative tangent of x times secant squared x dx plus the integral of, I'm going to write it as x to the 1/2 dx. Once you do that, it makes it a little bit easier to see how you might want to use a U substitution. So this guy is just going to be a straight up antiderivative using the power rule. But this one, we're going to want to use U substitution. So looking at this, tangent of x, its derivative is secant squared of x. So that's a hint that we're going to want to make tangent of x our u. So let's do that real quick. So I'm going to zoom in a little bit so that I have space. And let's see here. U is equal to tangent of x. And then du dx is equal to secant squared of x. So du is equal to secant squared x dx. So when we zoom back out and do this problem, we're going to rewrite it as the integral of e to the negative u times du, because secant squared dx is all of du, based on what we've got going on over here, plus the integral of x to the 1/2 dx. All right, so each individual integral has only one variable going on. This one has only u, this one has only x. So then when we take the antiderivative, oh, poo, I think I needed to do this for you guys. So I made a little mistake. What I want is actually negative tangent of x to be my u. So let's go back over here, and let's say u is negative tangent of x. And then that means that du dx is negative secant squared. So du is negative secant squared dx. So I'm going to erase my work over here a little bit. And so we're going to have e to the u times negative du. All right? Because this is equal to negative secant squared x dx. And so you can replace this with du, but you have to have that extra negative there. And then let's rewrite it real quick, just a little bit cleaner. So we have negative e to the u du plus the integral of x to the 1/2 dx. And then taking that antiderivative, the antiderivative of e to the u is e to the u. So we have negative e to the u plus, and then we go up, so it's x to the 3/2. And then dividing by 3/2 is the same thing as multiplying by its reciprocal. So we were going to put the 2/3 out front plus c. And so we definitely do not want to stop here because we have an answer that has u and x in it. So we want to go back to our original, or go back to how we defined u. And we're going to plug that in real quick. So that's going to be negative e to the negative tangent of x plus 2/3 x to the 3/2 plus c. So this is our final answer. And we started with this thing up here that was a little bit complicated, but it came out fairly straightforward once we messed with it a little bit. So we identified what our u should be. When we got a negative u here, went back and adjusted it a little bit so that we could go through. We replaced this with du, making sure that our signs were good, that our constants were good by factoring, and just went through and solved. Okay, now I want you guys to try to do these on your own. I'm going to let there just be dead time for 5 minutes. Last time I played really bad music, so this time I'm just going to have it be silent. So your time starts now. Okay. Oops. All right, so let's go through and see how you did. So for this first one, we should have identified that u is x squared plus 7. So du dx is 2x, which means that du is 2x dx. So we want 2x dx to be in our problem. So let's make a line here. Boop. Okay, so when we rewrite this, let's move that x to the back. And so we're going to have the square root of x squared plus 7. I'm going to leave a little space because we want 2x here, dx. But we only have x, so we're going to multiply by 1/2. All right, so we're going to have this kind of separate. So we end up with we end up with the integral of the square root of u times 1/2 du, which is 1/2 integral of u to the 1/2 du, which is equal to 1/2 times u to the 3/2 times 2/3. So that's just doing the power rule on u to the 1/2 plus c, which is ultimately equal to 1/2 times 2/3 is 2/6, so 1/3, or you could think of it as 1/2 of 2/3 is 1/3, times u, and u is our x squared plus 7, to the 3/2 plus c. And so this would be your ultimate answer. Probably should have left a little bit of extra space here. But yeah, that's how you would go through and do this. And so for the next problem, should have had u is natural log of x. So du dx is 1 over x, because the derivative of natural log is 1 over x. And so du is 1 over x dx. All right, so then when we rewrite this integral, you have the integral, and again, this 1 over 3x is similar to our 1 over x, so that is the one we're going to factor out. And so we're going to move that sign of natural log of x to the front, times 1 over 3 times 1 over x dx. So I just factored out that 1/3 from the 1 over x so that I can replace it. So this is going to be equal to the integral of sine of u times 1/3 du, because 1 over x dx is equal to du. So we have 1/3 times the integral of sine of u du. And then the integral of sine is negative cosine, so you have negative 1/3 cosine of u plus c. And then replacing the u with natural log of x, you end up with negative 1/3 cosine of natural log of x plus c as your answer here. So this is your final answer. One thing I want to point out with both of these is you have to watch the constants. A lot of times you can identify, especially when you get more used to problems that use the U-substitution, you can identify where you're going to end up with u and a du and what's going to disappear. But I would still go through this process and write it up because of these constants, this 1/2, this 1/3. You just have to be careful with them. That's where a lot of people mess up. So let's look at this last one. So this doesn't look like a U-substitution right off the bat. Unless you look at it in terms of, or you might be tempted to pull the bottom, the denominator, to the top by giving it a -1 power. But this plus 2 gets in the way of this. So you're going to pull it up, and then this whole thing will be to the -1, which you can do, but I'm going to leave it as is. And I'm going to just pick u to be 3x plus 2. So du dx, so the derivative of u, is 3. So du is 3 dx. So that's a number and 7 is a number. And so what happens when you factor out 3 from 7? Okay, so when we write this, bloop, we want to put it in terms of 1 over 3x plus 2 times 7 dx. But really, what we want is 1 over 3x plus 2 times 3 dx. So what do we need to multiply 3 by to get 7? And that is 7/3. Okay? So we divide 7 by 3 to get this. And so this will be our du eventually. So we end up with the integral of 1 over u times 7/3 du, which is, we can pull out that 7/3, integral of 1 over u du. And the antiderivative of 1 over u is natural log of u. So this is going to be 7/3 natural log of u plus c, which is equal to 7/3 natural log of 3x plus 2 plus c. And so this is our final answer. Okay, so another way that you could have viewed this is that this looks kind of similar in shape to 1 over x, just with some extra pieces. And so you want to get it into that 1 over x or 1 over u form. And so this is the process to go through to make it simpler. Almost always with U-substitution, when you use U-substitution, it makes things simpler with maybe a complicated constant that comes out. But it turns into a simpler problem. If you are using U-substitution and it becomes a more complicated problem, you probably picked the wrong U. So I'm going to give you 3 U-do problems with U-substitution. Just as a hint, you have seen one like this, just slightly different. This one, don't forget the plus sign. And this one is actually going to use two substitutions. So I would do substitution. So you do a U sub, and then might as well just do a V sub, because you're going to need to change letters. So see if you can figure out how to do this last you do. But let's go through and do the last you do. So a population of insects increases at a rate of 200 plus 10t plus 0.25 t squared insects per day, t in days. Find the insect population after 3 days, assuming that there are 35 insects at t equals 0. So we have that the integral is going to be of that rate of insects, so that's 200 plus 10t plus 0.25 t squared. And we want to see the total number of insects, so that total change from day over the first 3 days. So we're going to go from 0 to 3. But then we want to add that initial number of insects, so plus 35. Plus 35 at the end here. So when we take the antiderivative, you should end up with 200t plus 5t squared plus 0.25 over 3 t cubed, and you're going from 0 to 3 plus 35, which is going to be equal to 200 times 3 plus 5 times 3 squared plus 0.25 over 3 times 3 cubed minus, and then when you plug in 0 to this whole thing, it's just total going to be 0, because 200 times 0 is 0, 5 times 0 squared is 0, and then 0.25 over 3 times 0 cubed is 0. So the final answer should be, let's see here, 600 plus 9 times 5 is 45 plus 0.25 times 9, which should be 2.25. Yeah. Plus, I forgot to add the 35 on here. So plus 35, which is equal to 682.25 insects. Okay, insects. Again, you could round down, you can round up, or you can say that there's 0.25 of an insect. Maybe one of the insects is a larva. I don't know. But anyway, that is how to do the last you-do problem. That's it for this lesson. The next lesson, we're going to do a little bit more U-substitution, but this time with definite integrals. There's just a little bit more to keep track of. So, yeah.